This is video 16 in the lecture on the design of reinforced concrete beams. This lecture deals with cross-sections loaded with eccentric applied compression in domains 2A and 2B. The eccentric applied compression occurs in the domains 1B, 2A, 2B, and 3. In other words, in all the domains except domain 1A, where there is tension involved. If we look at all those domains which are applicable, then you see, in fact, on the left-hand side, bending is dominant. On the right-hand side, once the section is completely in compression, then compression is dominant. We will see that to choose the right formula, we have to know if the section is bending dominant or compression dominant. Now let's see what's happening in domain 2A. We have a rectangular section, doubly reinforced, and it's loaded with MD and ND. ND here a normal force. What we'll do is, to the center width of the section, we will see what is the eccentricity of the applied compression load and what is the total eccentricity regarding to the most tensioned reinforcement or least compressed reinforcement. It is always the same principle. At the bottom it's tension reinforcement, at the top compression. If the whole section is in tension, then the bottom is always the most tension side. And when the whole section is in compression, then the bottom is the least compressed side. It's just a convention to make it easy to make a drawing. So E0, it's the initial eccentricity. It is just the bending moment divided by the normal force. It's the normal eccentricity. So we work not with MD and ND, but we work with E0 and ND. And E1, the eccentricity regarding the tension reinforcement, it's, of course, if you look at the drawing, it's E0 plus H over 2 plus D1, minus D1, sorry. So you always need to make a little drawing in your head to arrive or to derive this formula. The bending moment we are working with to calculate the reduced bending moment is not MD, but E1 times ND. So that's a difference that we have to remember. So we work with the bending moment to calculate the reduced bending moment with the bending moment related to the most tensioned reinforcement. Now we have this section, we have the geometry, we have here the strain diagram that we are used now. Then we have the stress diagram, and from the stresses, the forces. So we will concentrate us on the forces. We have now, in addition to what we have seen previously, a compressive force in the compressed reinforcement. We start with the external forces MD and ND. We calculate the initial eccentricity with the reference the tensile reinforcement, and we calculate the MD for the reduced bending moment. So we concentrate us on the forces, and it's always the same system. We take a translation equilibrium. It means that the action, ND, equals the reaction. And the reaction is, of course, the compression in the reinforcement and in the concrete minus the tension in the steel. Then the compression force in the reinforcement is just the area of reinforcement times his stress. The compression component in the concrete is just the filling coefficient times the width times the depth of the neutral axis and times FCD, and then the force, the tension force in the reinforcement is then the area times the stress. Now if you look at this equation, we can regroup it a little bit. We will put the tension reinforcement on the other side of the equation, and then we regroup it with the stress in the steel. We put it outside the brackets, and you will see immediately why we do a thing like that. It will enable us to use existing methods to calculate reinforcement by just grouping it in this way. Then we have a look at the rotation equilibrium. It's a rotation equilibrium around the most around the reinforcement in tension. Now, in a lot of those calculation procedures, we will take a rotation equilibrium, and we often do that around the most tension reinforcement or the most compressed reinforcement. We always take one of the two. Then it's simple here. It's ND times E1. This is the external bending moment regarding this point, regarding tension reinforcement, equals the NC or the compression force in the concrete times the lever arm plus the contribution of the compression reinforcement. And the lever arm is then D, the effective depth, minus D2. Now, let's take a first case where there is no compression reinforcement. If we have that, we saw that we arranged the translation equilibrium to this equation. If we take AS2 is 0, then we have this equation. Now, this is a very familiar equation, because if you think that this term is equal to the area of reinforcement, then we see that it is exactly the same formula as we had for single bending. So that's interesting to see. If you look at the rotation equilibrium and we take AS2 equals to 0, then again we have a formula that we recognize. If you take NdE1 as the bending moment, the applied bending moment, then you will see that we can apply the same procedure for calculating reinforcement as used for simple bending, on the condition that for the bending moment we take ND times E1, not ND times E0, but ND times E1, and for the reinforcement we have the AS1 and plus ND divided by the stress. You will see here the physical meaning. If you have a normal force acting on the section, then your needed reinforcement is lower because of a term, your normal force divided by the stress. It's the contribution of the normal force makes that you need less reinforcement. So you can see it clearly in this equation. Now suppose that there is no compression reinforcement, and what we are going to do now is to explain the protocol that you need to calculate reinforcement in eccentrically applied compression. Just is the calculation by hand. So you always start with the eccentricities, the E0 and the E1. Then you calculate the reduced bending moment, take a tension, with respect to NDE1, not to MD, but to NDE1. Then we derive the mechanical reinforcement ratio and steel stress from the tables or from the formulas. But if you use a table, it's very easy. And you have the mechanical reinforcement ratio, and you look directly in the table at the stress in the steel. Then if you got the stress in the steel and you have the reinforcement, you can calculate the modified tension reinforcement, AS1. If we have compression reinforcement, then it's getting the procedure a little bit more complicated. You always start with the eccentricities. You calculate the reduced bending moment, but because we are talking about compression reinforcement, we suppose that you need compression reinforcement. That means that mu d must be bigger than a chosen value mu limit. The chosen value can be the one for rotation capacity or the one for yielding of the steel. You can in fact also say, okay, we don't use a mu limit, but we just put tension reinforcement without a specific goal. So it means that you choose a compression reinforcement, and by doing so, you can reduce a little bit mu d. We will have an example just now. Then we calculate the needed compression reinforcement. You can clearly see it is the bending moment minus the target bending moment. And just what I said now, if mu limit is not existing, then you choose A2 in such a way, or you choose mu limit as a number in such a way that AS2 is reasonable. In practice, we choose a reinforcement and calculate the other way around. Then we choose the compression reinforcement. This must be always bigger than the ones you have calculated. You can never round it down, otherwise you will not obtain your limit, your goal. Further on, we calculate the reduced bending moment with the chosen value of the compression reinforcement. This is real diameters and real numbers of bars. So you calculate now mu n. From mu n, again, we calculate the mechanical reinforcement and the steel stress. And if you got the steel stress, just pro rata, you know what ASC as reinforcement is. In most cases, sigma S2 equals sigma S1. And then we calculate the modified tension reinforcement for eccentrically applied compression with compression reinforcement. So remember this, that if you use compression reinforcement, you have a substitution, or you have a superposition of two states. Now let's see this procedure in an example, a very simple example of a section 300 by 600, a very typical section with reinforcement, tension and compression. It is loaded with 300 kilonewton meter bending moment and 700 kilonewton normal force. So when it is eccentrically applied compression, we start with determining the eccentricities. We first do this exercise without the compression reinforcement. It means we suppose there is no compression reinforcement, or the contribution of the compression reinforcement is neglectable. Then we see the primary eccentricity is 429 millimeters. It's just MED divided by NED. The E1 is equals 659 millimeters. Now, to give you an idea, if this is the section, this is the middle of the section, we see that the distance between those two is 530 millimeters. The distance at the bottom is 70 millimeters. E0, the primary eccentricity for the load of 700 kilonewton, is 429 millimeters, and the 700 kilonewton has an eccentricity towards the most tensioned reinforcement of 659. So now I have a clearer picture of how it looks like. The bending moment to calculate the reduced bending moment is then the 700 times the 659. And then we calculate mu n, it is this bending moment, nd times E1 divided by bd squared times FCD, and it's 0.322. And in the table or with formulas, you can choose, we calculate omega, and we have 0.405, and the sigma s is 435. And then we calculate the needed reinforcement. It is the reinforcement that we got from the table, which is 0.405, and then the definition of omega, minus, because that's what we gain by applying a normal force to the section, divided by sigma s1. We get 910 square millimeters, or we can say that's 3 diameters 20. So that's the first solution. We neglect compression reinforcement and we put 3 diameters 20 in the section. Now we can look again with compression reinforcement, then AS2 is not 0. But because we have a compression reinforcement and we do not have a goal to obtain something with that compression reinforcement, because this, it's not in bending, it's an eccentrically applied compression. So what we do is we choose from the beginning, we choose a compression reinforcement in such a way that the mu n, the reduced bending moment, is reasonable. Then we have the eccentricities, we already calculated them. Mn was then nd times E1, 461 kilonewton meter. And then we calculate mu n, and you see AS2 we already chose. We put 226, and we assume that the steel is yielding. If we do that, we have here 0.29, which is a very reasonable number as a reduced bending moment. Then from the table or from the formulas, we calculate omega and sigma s. So sigma s is 435, that's okay. And the xi, the depth of the neutral axis. And then we calculate ASN with the omega is 2203. And then we will look if the steel is yielding. For the tension reinforcement, it is just applying the rule of similar triangles. It is 4.4 per mil, so it's more than 2.17, so the steel is yielding. And for the compression reinforcement, we calculate also with similar triangles. It's 2.44, so it's more than 2.17, the steel is yielding. So what we assumed in the beginning that the steel was yielding is confirmed. If this was not the case, we redo the calculation with the steel stress that we obtain here. And then ASC is then pro rata, the reinforcement, but sigma S2 is the same to sigma S1, so it stays 226. Then the total reinforcement is then 820 square millimeters, which is also 3 diameters 20, but you can see we have too much reinforcement. So we can reduce this. We can try 4 diameters 16. It's a little bit short for 4 diameters 16. We can take 2 diameters 25, but that is even more. So we know we have a reserve, but we think 3 diameters 20 is the good one. Maybe we can combine diameters. That would be better. Then we have to check, of course, the beam width to see that we worked with 1 layer of reinforcement, and we check the total width of the beam with 3 diameters 20, and we see that the 3 diameters can be placed nicely in the section. So we have now at the end 3 diameters 20 as a tension reinforcement and 2 diameters 12 as compression reinforcement. In reality, when we have combined bending, what we do is we put as a compression reinforcement, we put the minimum required reinforcement in the section, and then we calculate, like we've done here, not just now, the needed tension reinforcement. Now we have eccentrically applied compression in domain 2B. in domain 2B, you can see that almost the whole section is in compression. So the compression zone goes at least over the whole area of D. So it means that compression is dominant. It's very important to recognize that. So when compression is dominant, you are in domain 2B. Once we are in domain 2B, then the depth of the neutral axis is almost larger. It's always larger than the effective depth of the section. So we are not working anymore with effective depth, but we are going to work with the total depth of the beam. So delta T1 is then equal to D1, the location of the least compressed reinforcement, divided by the total depth of the beam. The same happens with delta T2. This is for the compression side. And for the depth of the neutral axis, we are talking now Xi was X over D, but now when the compression is dominant, we call it Xi T of total. Xi T equals X over H, not D, X over H. Then it's always the same with the similar triangles. We can easily see what the strain in the tension reinforcement is and the strain in the compression reinforcement. It is easily calculated by those two formulas. Now we have a look at the total picture, the section, the strain diagram, the stress diagram, and if you see this, then you see in section 2B, we have always the full parabolic rectangular stress diagram, which is important because it means that psi, the filling coefficient, and delta G, that those two coefficients are constant for a given concrete grade. Then we have the forces. We must take care for the forces. For instance, in this picture, it's not entirely correct. You can see that this is drawn as there is compression and that the least tension reinforcement is in compression. So if you look at the arrows, this you can make it like that because it's a reaction. This is also fine, but this is not the opposite because all those forces here are reactions. This is the applied force action. These are reactions. So this arrow should go in the other way around. But it can happen. It cannot happen that sigma S1 is in tension, not in zone 2B. So this arrow should be pointed in the opposite direction. Then we have the action, which is the eccentrically compression force. It has an eccentricity E0 and an eccentricity E2 towards the most compressed reinforcement. So E0 we know, and then E2 you can easily see H over 2 minus E0 minus D2. You see the difference with the eccentric applied compression in domain 2A. Then we have an E1 and this is now an E2 because you are working towards the most compressed reinforcement. We have a translation equilibrium. It's very easy. It's just the normal force must give an equilibrium with the force in the concrete and the forces in the reinforcement, compression and tension. You see this sign is okay because sigma S2 and sigma S1 are always compression and it's the same as the compression in the concrete. Rotation equilibrium around the most compressed reinforcement. It's always the same. It's the same kind of formula. So it's the equilibrium around this point here, around this point here. Now, if we take this equilibrium, rotational equilibrium, and we are going to play around with it, and we take this term of this portion and we put it on the other side, and we have this. Then we divide by BH squared FCD, and we define mu D as this term. This is equal to mu D. You notice that it's H squared, not D squared, because we are in compression, in dominant compression. So if you take now mu D equals this, and then we take the delta T2, the definitions of delta T2 and Ct into account, and we substitute it in this equation, then we got a similar equation that we are very familiar of, and a very simple equation. You can also inverse the equation by taking out Ct, and then we have this nice equation. So what you can do now is, by calculating mu D, which is this one, you can, and delta G and C are constant for a certain concrete grade, so you don't have to integrate. It's because we know that we are in an area where the parabolic and the rectangular stress diagram of concrete is fully developed, and we calculate the position of the neutral axis. What's the protocol now? How to calculate it by hand? We just start with the eccentricities. Then we do a first iteration. We suppose that the stress in the least tensioned or the least compressed reinforcement is 0. Why? Because it's totally at the bottom, and there is there's a very little strain at the bottom. So the best guess is that you take a very small figure for the first iteration of the stress in the steel, which will take 0. So the reduced bending moment is then NdE2. Remember that all the time. It's not MD, it's NdE2 divided by BH squared FCD. Again, tension H squared and not D squared. Then the filling coefficient and the coefficient of center of gravity for concrete grade smaller than C50-60, it's always 0.81 and 0.416. There are tables for high strength concrete, but this is constant for a constant concrete grade. Then now we calculate the depth of the neutral axis, because all this is now known. Then we want to know what is the strain in the reinforcement at the least compressed reinforcement and most compressed reinforcement. We have some variables too much, like delta T1 and delta T2, which is the position of the reinforcement to the most compressed and most tensioned fiber. Most of the time the concrete cover on the top and the bottom is the same, so we will take delta T1 equal to delta T2, but it's not necessarily the case. In reality, you suppose it's the same. You start with a value, you do the calculations, and when you have calculated AS1 and AS2, then you can calculate the exact delta T1 and delta T2, and you restart the calculation. So then we have the strain in the reinforcement, and we calculate the stress in the reinforcement. When we got the stresses in the reinforcement, we can calculate the compression reinforcement. It's in fact simple. If you take the translation equilibrium, the very simple translation equilibrium, you rearrange the terms, and we still have in this equation AS1, AS2, sigma S2, sigma S1. We have one variable too much. So what we will do, it's just a small trick. We say that Chi equals the proportion of the two reinforcements. If we do that and we replace AS1 with Chi AS2, then we have a formula to calculate the compression reinforcement, but we still have the factor Chi. So what do? If you have a symmetrically reinforced section, you take Chi equals to 1. If you have a certain goal in mind, that's possible. You can say it must be 1/4 or it must be 1/10 or anything. You can put a number in it, and once you've got a number, you calculate the compression reinforcement. It also indicates that the solutions are endless. You can have any combination of AS1 and AS2. After you have done that, you got now AS1, AS2. Now we are going to do a second iteration. But the second iteration, we do that with the calculated compression reinforcement and with the calculated steel stress. So the first iteration was NdE2 divided, was NdE2 divided by BH squared FCD. But now we subtract a term of that because we know now what is the AS1 that we just calculated in the first iteration and what is sigma S1 in the first iteration. So then we calculate again the depth of the neutral axis. So this is now the mu d of the second iteration, the mu d of the second iteration. We have then xc t of the second iteration. We calculate the strain in the second iteration. And then we can calculate the stresses in the second iteration. And then after that, we can calculate the compression reinforcement. And then we do the iteration again, if needed. If sigma S1 and sigma S2 are different, then we can again make an iteration. Most of the time, after 2 iterations, it will be fine. What is important in this method is that we use psi and delta G as a constant value. This is only valid, all those formulas, in the domain 2B. How do we know that you are in domain 2B? Remember, it's eccentrically applied compression. It's not simple bending, so we don't know the border limits, but we can calculate them. The left border, that's easy. That's when Ct is 1 minus delta T1. That's the depth of the neutral axis. The right border is when the depth of the neutral axis is equals to h, so Ct is 1. So that's the left border, and then we can find the reduced bending moment for the left border for concrete grade smaller than C50-60, and I assume that the delta T1 and delta T2 is equal to each other, and it's equal to delta T, which is this delta T. So you can have a closed expression, if you assume this, for the left border and the right border. So every time you calculate reinforcement, you check your mu d, and it should be between those two values. And then you know you have applied the right formulas. Let's take an example of a concrete section, and there is a bending moment of 320 kilonewton meter and a normal force of 2,900. It's a normal section, 600 by 300. Now, you look at this. You should immediately notice that compression is dominant. So don't use the formulas of zone 2A because it will not work out. You can have a feeling that most likely you are in 2B or in zone 3. That's in domain 3. That's also possible. To make it easy for us, we will take D1 and D2 equal, and we fix it to 70 millimeters. If you do not this, then you calculate the reinforcement AS1 and AS2 with an assumption of D1 and T2, and at the end you recalculate it with the correct value. This is a little bit tedious, and that's why, to make it a little bit easy for us, I fix it on 70 millimeters. And then we have to calculate the reinforcement, compression and tension reinforcement, but there's one condition: the tension reinforcement is 1.5 times the compression reinforcement. So we can follow the different steps. We start with sigma S1 with the stress in the tension reinforcement, and we know that we have to start with a low value. Here normally we start with 0. Here we started with 100, but you should never take more than 100. So we started with 100. We calculate E0 and E2. After that, the first iteration of the reduced bending moment, which is 0.189. Oh, now we must take care. What does that mean? We calculate the left border of the domain 2B, which is 0.179, and the right border of the domain is 0.24. So we are in domain 2B, so we have the right formulas. Then we calculate the depth of the neutral axis. We know C and delta G, which are 0.416 and 0.81, because the whole area of the parabolic shape and the rectangular shape of the compression of the stress diagram of the concrete is there. And once we got CT, the depth of the neutral axis, we can calculate easily the strain in the reinforcement and the stress in the reinforcement. And we see in our first iteration, the stress is 15 megapascal. So we started with 100 and we end up with 15. That's for the first iteration. So now we'll do a second iteration. That was the first iteration. Now we do the second. We start with 15 because we ended up with 15 here. And we do the calculation again. Now remember, the mu-d is now corrected because it's the second iteration. It's corrected with this term because we know now AS1 is here, and we know sigma S1, which is this one. So that's why we have to modify mu-d. Again, now it's 0.18. We are still in domain 2B, so it's fine. We do the calculation again. You see here that we use G equals to 1.5 because the tension reinforcement was 1.5 times the compression reinforcement. And we have here 8. So we start with 15, we have now 8. Now we start with 10, we do the calculation again, and this is right. The iteration is okay. So you will see now that AS2, we can apply 3 diameters 16 and 3 diameters 20. Then we have 1546 square millimeters. Okay, that's close enough. And for the tension reinforcement, 3 diameters 20 and 3 diameters 25. We can now calculate the reinforcement needed at eccentrically applied compression. See you at next lecture.